In this video, we'll talk about finding higher order derivatives using implicit differentiation. So we can use implicit differentiation for pretty much anything we could do before with derivatives. That also applies to finding higher order derivatives. The main point in how you know this is the fact that if I take the derivative of y prime, or in the other notation derivative of dy dx, this gives me y double prime, or the second derivative. So the way I get to a second derivative is by differentiating the first derivative. The main way to think of this out is you're going to want to solve out for y prime first, and then differentiate the equation again to get to the second derivative. If we go back to our circle example, we saw that we had that y prime was negative x over y. Now I want to differentiate this again to get the second derivative. So I apply a derivative to this equation here, and I get that on the left I have y double prime. This one is more explicitly defined, so you're always going to get y double prime on the left here when you solve it out this way. What does this equal? This equals the derivative in x of negative x over y. Well, that's a quotient rule because x and y are both functions here. So by the quotient rule, I will get low d high, the derivative of negative x is negative 1, minus high, which is negative x, d low, dy dx, over y squared. But now, what is dy dx? Well, I need to bring this equation now back in here to actually see what's going on. So I can now plug in my formula for the derivative into the second derivative. This is going to be a common theme for these problems, that you will need the first derivative formula at the end to evaluate the second derivative. So I can plug that in, and I then get that negative y minus x squared over y. If I plug in this there, what I get, divided by a y squared, and that is going to be my second derivative here. You can do some more manipulation if you want to get to something like negative y squared minus x squared over y cubed. And the use effect that I know that x squared plus y squared is 25 to get a negative 25 over y cubed. But that's the idea. The idea is you want to get to the first derivative, then differentiate that again, get the second, and you're likely going to need to plug back in the first derivative equation to get the final answer. Because you want your final answer here to only involve x and y, not involve dy dx. Let's see one more example. Find the second derivative of y with respect to x for y defined implicitly by the following formula. We did the first derivative of this before, but we'll do the whole process from the start to see what that looks like. I have my implicit function here. I need to differentiate the whole thing with respect to x and see what I get. So differentiate. This gives me a 4y cubed dy dx from the first term, a minus dy dx from the second term, equals a 3x squared plus 1. Now you could, at this point, differentiate again, get to dy dx squared, and then solve out. That's going to be a little more complicated because this is a product rule, and you're still going to have to eventually solve for dy dx anyway, because it's going to show up in your answer. So your best bet is likely to simplify out first, solve for dy dx, and differentiate at that point. We can solve out again. This gives me dy dx equals 3x squared plus 1 over 4y cubed minus 1, just by factoring out and then dividing by the 4y cubed minus 1. Now I can differentiate this. When I do that, I will get a d squared y dx squared on this side, which is good, that's what I want. And over here I have the quotient rule. So low d high is 6x minus high d low is going to be a 12y squared dy dx, and then divide by the bottom squared. That 12y squared comes to the root of 4y cubed, and then dy dx shows up by the chain rule. So now I want to plug this formula into dy dx, and then try to simplify. So I will get that my second derivative equals 4y cubed minus 1 times 6x minus 12y squared times, now since dy dx has the 3x squared plus 1 on top and the 4y cubed minus 1 on the bottom, I'm going to get a 3x squared plus 1 squared and a 4y cubed minus 1 to the minus 1 comes on the bottom, divided by 4y cubed minus 1 squared, which is good enough. I could also just get rid of this minus 1x by moving to the bottom and rewrite this as d squared y dx squared equals 6x times a 4y cubed minus 1 squared minus 12y squared 3x squared plus 1 squared over 4y cubed minus 1 cubed. And that gives the expression for the second derivative here in terms of x and y. So if I gave you a point on the curve, you could then tell me what the second derivative was at that point, if it's positive or negative, or what kind of number you get, just by plugging x and y into this function here. That's the basic idea of using implicit differentiation to find higher order derivatives. The basic idea being you want to solve first order problem out entirely first, solve out for dy dx y prime equals stuff, and then differentiate that a second time to get to the second derivative, so you can analyze these sorts of implicitly defined functions using all the different tricks you have for derivatives at this point.